There we go. Pamela, can you hear me? Is this on? You're muted. Still muted.
Yeah. So when I produce Hangouts, I unmute the people I mute.
You can't do that.
Yes, you can.
Really? I
Do
can
you
mute you
not
and then
use...
unmute you?
Yes, do you not use the control room?
No. No.
Silly boy.
Should I? Okay, well maybe I will next week.
That way you don't ever have to worry about someone forgot that you had muted them and is talking. You just unmute them when you see their lips moving.
Or just leave them muted for hilarity. Well, hey, Pamela, how's it going? How's the weather there in the frigid Edwardsville area?
Yeah, it's kind of blowing snow and blowing winds and blah and blah.
Well, there was a great prediction of this. There was this amazing storm, like hurricane strength level storm that struck Alaska and just pushed all this Arctic air down into Canada and the United States.
Yes.
And pretty much the entire continent is in a deep freeze right now. We're not bad. We're sort of hovering around freezing here in Western Canada, but I know
Yeah.
you've got it pretty cold there.
Yeah, it's 10 degrees Fahrenheit, which is well below 0 in Celsius, and we're getting 20-mile-per-hour winds, which are 30-kilometer-per-hour winds, and yeah, it's gross. I'm glad I'm recording from home. Although I turned off the space heater for the sake of our audio quality, so I'm going to slowly get colder and colder and colder throughout this recording.
Now, I don't know if you heard, but we landed on a comet.
We did. We didn't just land. We landed 3 times, although one of them kind of included bouncing off of a cliff into a hole. But that's okay.
Yeah. What a week. This was us living Curiosity all over again, but better.
Well, and the thing that I don't think people fully comprehend is, with Curiosity, that was a modern spacecraft that has been built in the past few years. It took it like half a year to get to Mars. Everything was new and shiny and bright. With Rosetta, they took that spacecraft, they started conceiving of its designs 30 years ago, launched it more than 10 years ago, put it into hibernation cycle. So you know that button on your computer that says put hard drives to sleep but wake up for network activity? They did that to a spacecraft.
Yep.
And they planned to land on a spherical-ish, ellipsoidal, snowball-shaped comet, and instead got a rubber duck. And they still managed to figure out how to make things work. And that is all kinds of awesome. The lesson that came out of this is the universe is more screwed up than we know how to plan for.
Yeah. And boy, I mean, the folks on the mission just did a great job. The ESA folks just getting the word out did a great job, except for one huge bone of contention, which I have, which is that the data from the OSIRIS instrument wasn't released, except for a few tantalizing, amazing pictures.
I know.
Yeah.
And kudos to the team that did the illustrations for Rosetta and Philae.
Yeah.
Oh my gosh, those were adorable. And they had the checklist going throughout the entire process. So yeah, it was just kudos.
And I called it. I don't know if you recall last year. Actually, we were all talking about this. Like about a year ago, we were all so excited about this was going to be the big one. Rosetta was going to be the one that we were all going to be really excited about. And the fact that there was so many great stories come out of it, that it was orbiting, that it was, that it had to orbit for a while and catch up and take better pictures and then land, and all the time of the landing was so tense. Yeah, so we're going to go through this again twice next year. We've got...
sort of. Dawn and New Horizons don't have accessories that they're planning to perch precariously on icy bodies.
Yeah, but that's exactly it, right? New Horizons, we're going to see Pluto for the first time next year, and then Dawn is going to reach Ceres and start orbiting an icy asteroid for the first time. These are both really exciting, and we're going to get to go through this all again, so I can't wait. We should do a show.
We should.
All
we
right.
should. It's getting cold in here. I can actually feel the temperature dropping.
Oh, you put on more layers. Okay, cool. So for those of you who have no idea what we're talking about, this is Astronomy Cast, our weekly space show. So we're going to do the show. We'll take about half an hour, well, 27 minutes actually, and then when we wrap that up, we will take your questions about space and astronomy. And I know you're going to want to talk about Rosetta. So if you don't want to talk about our topic of the day, which is Sandra Faber, you can also talk about Rosetta or really anything that interests you in space and astronomy.
You just have to wait 28 minutes.
You just have to wait. Yeah, exactly. Yeah, but go ahead and start posting your questions. And the place you can do that is in the Q&A app, which should be available wherever you're watching this video. It should say Fraser Cain is taking questions from the audience. Click there, and I can see the Q&A app is going. I can see posts from people. So it's all happening.
And
Let me know.
I'm trying to figure out where I hid Twitter. Wait, there it is. Hi,
You don't need Twitter. Twitter's no good to you. Okay, let me know when you're ready.
I am ready.
Okay, I'm going to press record.
I have pressed record, and it is recording.
Awesome. All right, here we go. Astronomy Cast, episode 358, Sandra Faber. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
Good. We landed on a comet.
We bounced around on a comet.
It's still there. In the end, it landed.
It did.
Yeah.
But the fact that it bounced around is even more awesome than the fact that we landed there.
Yeah, and like literally as we're recording this, there's some pictures now of Philae's various bounces and movements across the surface of 67P. So it's just what an amazing week this has been in space and astronomy. So
it almost makes up for the prior week, and as Emily Lakdawalla beautifully put it, robots exploring space is human space exploration, where the robots are our eyes, our ears, our hands, and we need to celebrate these wins and consider how much more we can do by welcoming our robot overlords.
Right. And if you love this, next year, 2 more missions, right? New Horizons going to Pluto, Dawn reaching Ceres. It's going to be another good year for this kind of robotic space exploration. So hang tough. It's going to be fun. All right, well, let's get cracking with this week's episode. So our focus on female astronomers continues with Sandra Faber and Professor of Astronomy at UC Santa Cruz. Faber was part of the team that turned up the Great Attractor, a mysterious mass hidden by the disk of the Milky Way. All right. So let's get cracking. So this is part 2, Pamela, of our journey into investigating the lives of some modern women in astronomy. Actually, someone recommended. I think Guido Bieber recommended that we also focus on female astronauts down the road. That might be kind of cool too.
Yeah, we've never discussed astronauts.
We haven't discussed any astronauts, actually. So all astronauts. Yeah, we should do a whole other series on astronauts. That'd be awesome. Okay, so Sandra Faber. Who is she?
She is a woman astronomer who's alive and has done amazing things. Like me, she's from Massachusetts. She, according to her Wikipedia page, is from Boston, which a lot of people write Boston even when they're from all sorts of other surrounding places. So I can't say she's necessarily a Bostonian as much as she's from Massachusetts. She went to Swarthmore as an undergraduate, went to Harvard as a grad student, graduated there in 1972.
Did somebody else go to Harvard as a grad student that I know?
I didn't go there for grad school.
You're a postgraduate school, right?
I was an instructor there. I was
at Harvard.
Yeah, and she was actually one of last week's. Last week we talked about. My brain just broke completely. We talked about Vera Preston.
Oh, well, Vera Rubin last week. Yeah.
Thank you, Preston.
Yeah, sorry.
Make me sound more intelligent than I am. Um, so at Harvard, Sandy Faber was actually one of Vera Rubin's grad students, and from there she's gone on to have an amazing career where she has bridged both doing amazing science and working on the instrumentation necessary to enable that science. And there aren't a lot of people out there who are both on the making sure the instruments get built and on the making sure awesome science gets done. They work collaboratively all the time, but she is someone who's driven both sides of that equation, working simultaneously on the development of the Keck telescope as well as on the Wide Field Planetary Camera for the Hubble Space Telescope. And she may have been the only person insane enough to do both of those things at once.
Now, everyone's favorite pictures from the Hubble Space Telescope, many of them were taken by the Wide Field Planetary Camera. Like that's one of the ones that takes some of the prettiest pictures from Hubble.
It has since been supplanted by a whole series of instruments, but that was that first big color image, beautiful pictures, gorgeous, weird corner chopped out of it. That this is a Hubble image because it has a weird shaped camera. That's the WIFPIC camera, and she actually had taken a year off to work on the East Coast. She'd been out in California as part of the UCal system and went to live out east working at the Space Telescope Science Institute when they realized, holy expletive, Batman, something's really wrong with Hubble. And it was her team at Space Telescope Science Institute that worked hours upon hours that we probably don't even want to think about, trying to understand what had gone wrong and how to fix it. And then years later, she was one of the people who went to the National Academies and worked her butt off arguing, well, we fixed it, now let's keep it in orbit and keep upgrading it, because after the Columbia disaster, there was plans to scrap the refurbishing mission, and she fought to figure out how do we get one more shuttle to fly to the Hubble.
Now, you've jumped around a bit.
I have.
Yeah, so let's go back
I'm
a bit.
excited.
No, it's great. It's great. I mean, what a phenomenal body of work. So let's go back to sort of, some of the earlier stuff that you worked on. As you said, working with Vera Rubin on motions of galaxies, right?
Right, and from there she went on to be one of the names behind what's called the Faber-Jackson relationship. This is a relationship that was noticed in elliptical galaxies. These are the ones that look kind of like a big old swarm of stars rather than having the pretty spiral structure like Andromeda does. She found, along with her collaborator, that in big ol' elliptical galaxies, there is a relationship between the rate at which stars are orbiting around the center of that galaxy and the surface brightness of that galaxy. And this allows us to start to get at, well, how far away is the galaxy? If you know how bright it appears to be, you can get at how bright it actually is using this relationship by measuring the rate of stars going around, which has nothing to do with how far away it is.
Right. So it's like another one of those cosmic yardsticks that.
It's not the most accurate of them, but it, along with the Tully-Fisher relationship, which works in spiral galaxies, these two different relationships are a first-order estimate of this elliptical galaxy, this spiral galaxy is further away than this other, with fairly large error bars. And the Faber-Jackson relationship also started to get at what we call the fundamental plane for elliptical galaxies. And this is this phenomena that has since been very well mapped out that describes if you have a big old elliptical galaxy, the bigger it is, the faster stars will be orbiting its massive center. So you have this increase in orbital rate, the dispersion of the rate at which stars are seen to be going around. You also, for more complicated reasons, these have lower surface brightness. So if you have a small mass elliptical next to a large mass elliptical at the same distance, and you look at their how bright they are per square pixel, the big one is going to be much more spread out, much more diffuse, and have a lower surface brightness. But because it's so much bigger, it's going to have a much larger total luminosity. So you have this larger total luminosity, larger rate of stars going around, larger mass, lower surface brightness. All of this gets tied together, and we use this to define a plane that cuts through the parameters of luminosity, surface brightness, and velocity dispersion.
And so, you've got this situation where the yardsticks that work there, like Type 1a supernovae, you can't count on them to go off in the galaxy that you're hoping to study, right?
Exactly.
So if you haven't, if you do get one going off in an elliptical galaxy, now you've got some corroboration, and you can test your different methodologies. I guess the other method that works at that range is the Hubble
flow.
The Hubble flow, the Hubble constant at that point, right? And so the two can kind of help you get at the distance. But
and a large part of what she's done throughout her entire career is trying to figure out how galaxies trace out the large-scale structure of our entire universe. She is actually one of a small group of what are called the 7 Samurai. These are 7 scientists who are responsible in the 1980s for measuring how a bunch of different galaxy clusters and large-scale structure appeared to be flowing towards this thing that is blocked by the disk of our Milky Way galaxy. And this
is it UFOs?
No.
It must be UFOs, right?
We call it the Great Attractor.
Is it a dimensional portal to another
some people
space?
write papers like that. You're triggering bad thoughts. Anyways, these seven individuals, David Burstein, Roger Davies, Alan Dressler, Sandra Faber, Sandy Faber, however you want to call it, Donald London Bell, Roberto Turlevich, and Gary Wegener, they all work together studying how galaxies are unevenly spaced throughout the universe and looking at their flow as they appear to have motions that are superimposed on top of the motions that you anticipate just from the expansion of the galaxy. This additional motion on top of, the expansion of the universe. This additional motion that is on top of the expansion of the universe has to come from something. It's gravitational attraction generally. Our own local group is falling into the Virgo supercluster. And then 7 Samurai discovered all of these things falling into the Great Attractor, which, like I said, it's hidden behind the disk of the Milky Way, so we can't actually see what it is, which is really annoying. But whatever it is, looking at the flows of everything towards it, it's about 250 million light years away. It's in the constellation Centaurus. And it's just really annoyingly in the disk of the galaxy where we can't see it.
But it's another one of those things, right? Like, it's been given the name the Great Attractor, and it's like dark matter, dark energy, black holes. You get this name, and it just conjures people's imaginations. And so if you just said there's a galactic supercluster that away, and
that we can't see
because it just happens, like bad luck happens to be that it's on the other side of the core of the Milky Way, which completely blocks our view. But the galaxies above the Milky Way and below the Milky Way are all sort of sliding towards this Great Attractor. But it is just a large galaxy cluster. Like, don't panic.
Yes,
It is not
it
going to tear a hole in the fabric of the space-time calliope.
no, no, and it's really kind of crazy the way people have written some of the most insane papers about all the things the Great Attractor could possibly be. And no, it's just a giant galaxy cluster we can't see. That's it.
Right. Okay. So Sandra Faber worked on really identifying this motion and helping to really show that there is this strange motion of all these galaxies. And just sort of one thing, in the kind of the modern age with these modern infrared telescopes, astronomers have been able to see more and more through this dust and gas that's clogged the disk of the Milky Way, and so they're really narrowing in exactly where this thing is and kind of what it is. So it's becoming less and less mysterious all the time. Again, don't panic.
Yes. We need a big happy yellow sticker.
Yeah, don't panic. Great. Okay, so worked on that. What else?
So that was what she did in the early 80s. In 85, she began work on the Keck telescope, working on one of its spectroscopic instruments. This is an instrument, DEIMOS, that would allow the redshifts of galaxies to be readily determined with high precision. And this is the type of data you really need to start mapping out in even higher detail the galaxy motions that she'd already been working on with her work with the Seven Samurai. About the same time, she joined in the team that was building the Wide Field Planetary Camera for Hubble. So here she is working on the Hubble Space Telescope's imager and working on one of Keck telescope's spectrographs. All of this in hopes of getting amazing data later on that would allow her to continue mapping out the large-scale structure of the universe. Now, while Keck went along at a fairly good clip and went fairly successfully, although they had a lot of issues initially with their multi-mirror system, nothing big to stress out about. Hubble didn't quite have as happy a beginning as one might wish.
Well, it's important to note, I think, Keck is, until like just recently, the biggest telescope in the world.
Yes.
Right? It's a monster, 10-meter telescope in Hawaii, top of the line, adaptive optics. You couldn't work on a finer instrument and use it for a more powerful purpose. So the fact that she did that, and then also worked on something that would do even better than the Keck telescope, the Hubble Space Telescope. But yeah, and so all these hopes and dreams, launched the Hubble Space Telescope. First images came back, and
no. The universe said no. So as Sandy's work figured out, when they ground the Hubble Space Telescope, they didn't grind it precisely right. They brought it to a focus in the wrong place. So while it had a perfectly ground mirror, it was perfectly ground to the wrong specifications. And that meant that in the optical assembly that it was part of, they couldn't get the telescope in focus. And not being able to get a telescope in focus, and in this case it wasn't that it was just out of focus, move the eyepiece in and out, moral equivalent of moving the camera in and out. No, it had a nasty stigmatism. So this is where different parts of the mirror focused in different ways. And they were able to figure out how to fix this by putting a new corrector lens packet in, but that required a second space shuttle mission. And it was not easy to figure out all of this. And in between these two instances, we also lost the space shuttle program for a few years. So her career was not an easy one, you might say.
Yeah, yeah. So, I mean, the Challenger, I'm trying to think the timeline, right? Um, so the Hubble was launched, I think, 90,
No,
95?
Hubble was launched April 24th, 1990. So
1990. Okay,
so
so
it came after Challenger.
after Challenger, yeah.
It was one of the first big launches after Challenger. But okay, let me rephrase that. We didn't lose the shuttle program as much as we lost the planned ability of the shuttle to go grab Hubble and bring it back down to Earth. So Hubble was built and designed prior to Challenger. And Hubble was designed that it could be put back into the cargo bay of the shuttle, brought back down to Earth, and have its instrument packs swapped in and out. It was designed to have new instruments put into it. It was designed to have upgrades. Now, the problem is that after the Challenger disaster, it was decided that it probably wasn't safe to bring down heavy telescopes, or anything else for that matter, to the planet Earth. This meant that we stopped running the space station-like things, the space labs that were in the cargo bay. We didn't bring things back down to the planet. And that means we couldn't bring the Hubble back down to the planet to fix and repair. And we had to figure out, I was in high school, so I had nothing to do with this. People like Sandra Faber had to figure out, how do we, while in orbit, while dealing with astronauts in gloves instead of technicians in, well, just latex gloves, which are different than space gloves, how do we figure out how to add in a whole new optical kit it wasn't designed for, fix this horrible aberration, and get it back to doing the spectacular science that it was designed to do?
Yeah. Okay, so that kept her busy.
So they were able to get it fixed, and they did get Keck, which Keck Observatory is actually two telescopes. So just to make that extra clear, these are two giant telescopes that were among the first telescopes to use segmented mirrors. They weren't the first, but they were among the first. So she's dealing with brand new orbital technology that flew flawed and had to be fixed. She's dealing with fairly brand new Earth-based technology, and at the same time producing amazing science.
And she's still, I mean, she's still working.
Yeah, she's 69 years old and still going strong, still sitting on panels, still teaching classes, still doing research.
And she won a pile of awards.
She has. No Nobel Prize. I don't think there's any women alive in physics astronomy who've actually won a Nobel Prize, which is a little sad. But I think she's won just about everything else you can win, which is kind of cool. And she continues to lead teams, which at a certain point, when you get to lead the team, that means you get all the paperwork. But it also means that you get to make sure the science that you want to see accomplished is what gets accomplished. And today she's the leader on the Candles project, which is continuing to map out at ever higher redshifts, at ever greater resolutions, the large-scale structure of our universe.
That is awesome. So again, I gotta ask, have you met her?
Yes, actually I have. I got to meet her when I was a graduate student. She came out to the University of Texas, gave a great talk, and then spent some time sitting around with us graduate students. And I was just a baby graduate student at that point. I was first or second year. And telling us what it was like to work in all of these high stress environments. And it was one of those conversations that kind of leaves you going, oh great, I thought grad school was really hard. Apparently this is the easy part. But then to listen to her, it was just like, if you believe in something and you are curious and you need to know the answer to your science problem in order for your life to be happy, she didn't phrase it this way, but the message I took away from it was, if you really want to know the answer to a problem, it's worth putting in the time. It's worth living through the stress to get at those answers to those problems, to those scientific questions. And the other thing that she did that really impressed me is she did all of this while being a mom. And you don't hear about that a lot. What you hear about a lot is the woman who decided to put her science career ahead of having children. She didn't do that. She had the family. She did the engineering. She did the science. And while on one hand it's kind of a bad thing to say that a woman has to try and do it all, she is one of the women who did manage to do it all. And while she didn't always make it look easy, she made it look like it was worth trying to do, because great things are possible.
Yeah, yeah. It's like, I mean, you don't have kids. I have kids, and it is always hard, and there's never a time when it's easy. And so, and to definitely to balance those things all out, partly keeps you grounded, you know, in making sure that you remember why you're doing a lot of the work that you're doing. Now, you know, I haven't been discovering enormous new universe galaxy clusters, but you know, the work is ever present, and you always have this tension between the work that you're doing and the family life, and I think the two definitely sort of influence and help each other out.
Yeah, I don't have kids, but I have a horse, and I know that sounds like a stupid analogy, but like this morning I was out at the barn, and the horse I've been leasing, I don't actually own her, the horse I've been leasing was having a complete freak out because snow and things and stuff on the roof. Crazy horse. And I had work I had to do, and it was like, okay, I have to make choices. And that's nothing like the choices you have to make when you have children, but Cosmic Quest is really my child. It's my vision, and just trying to have a horse is the limit of my capacity.
Yeah.
I look at the people who have actual children rather than furry children, and I killed all my fish during the International Year of Astronomy. I didn't mean to.
Right.
My tank died brutally. I haven't had fish since the International Year of Astronomy. I don't know how she did it. And this isn't me being blasé. This is me saying, quite honestly, as someone who runs a research team and glued myself to the chair I'm sitting in right now for the past 2 weeks to write grants and everything else to keep my staff funded, I don't know, in all honesty, how someone accomplishes everything that she has accomplished in her life and remains sane. And she was perfectly delightful to work with, and from what I understand, she's the kind of person who knows when to be tough as nails and draw a line in the sand because something's important, and when to just be nice. And that's a really hard balance to have. And that was my one experience with her, and that's what I've always heard.
That's really cool. Cool. Well, thank you very much, Pamela, and we'll continue on this conversation next week.
Sounds great, Fraser.
All right. Stop your recording.
Yep.
Save.
And I did have total horse freak out this morning. Oh
Did
my
you?
gosh. Yeah. It was several of them. They did not appreciate the snow. I keep my horse out at a barn where there's a bunch of other horses, and they were having nothing to do with.
Yeah, they need more experience with snow.
It's the snow they're mostly okay with, other than it's shiny and white and new and oh my god. But when it starts blowing across the roof, oh man, they're calling in the National Guard to St. Louis. Joy, I'm not leaving the house.
Okay. Have fun with this. Thomas Traneker asks, can you get her on Astronomy Cast? That would be cool.
We may have actually had her on one of the Q&A episodes from a conference. Right now I'm not traveling very much, but if I get my travel going back again, yes, I'd really enjoy the opportunity to interview her. Or if I think it would be kind of added to our workload to start adding interview shows along with our normal weekly shows. But if we do start doing that, or maybe on the weekly Space Hangout would be a more relevant place.
Yeah, it would be great. I mean, all the times when we've had special guests on, I mean, the problem, like with the Weekly Space Hangout, it's an absolute treat, and I really enjoy having them on the show. It's just a matter of reaching out to them, asking if they're willing to be on the show, and then bringing them up to speed on the technology and helping them get set up with the, it's just, I sound like I'm whining. Yes, I'd love to get people like that on the show. I can't wait. We're totally going to do it. Hey, have you read The Martian yet?
Yes. It's awesome.
God, it's such a good book.
I have to admit, I actually listened to the audio version because.
So did I.
Okay.
Yeah.
The book has the science so incredibly right, and a lot of the politics feel true. And read it if you haven't, dear audience.
Yeah, and so this is The Martian by Andy Weir, and it is going to be made into a movie. I don't know if you've heard.
Really? No.
Ridley Scott is directing the movie.
He's perfect.
Yeah, I know, and Matt Damon is going to be the main character.
Not as perfect, but cool.
I think it'll be great, and I mean, I love the main character, and so it's I'm really excited. I'm more excited about this than I was for Interstellar, and which I think you probably still haven't seen.
I haven't.
I
haven't left my keyboard for 2 weeks.
I know. Get back to work anyway. Yeah. Who let you get talk about anything other than your research grants?
If you want me to go see Interstellar, donate enough money that I don't have to freak out about my staff.
Where can people donate?
Go to cosmoquest.org/donate. And we are in the process of looking for corporate sponsors. If you have any contacts, I'm going to be starting to write letters to corporate donors this week. Potential corporate donors. We don't actually have any right now, so this is entirely new for me. But NASA grants have gone away, just flat out gone away. And I'm chasing National Science Foundation and everything else. But we're looking at anywhere from 1 in 20 to 1 in 8 odds for every grant we write.
Fortunately, you're the best. So.
Yeah, but I got the last grant that I got back. My reviews were excellent, recommended for funding, not funded. There's nothing worse than getting a rejection letter and reading your reviews and seeing written in your reviews, recommend for funding.
Yeah, this is perfect. Absolutely fund it. Not
makes
funded.
You cry.
Yeah. Okay, Bob Harkins asks, would not the Great Attractor have had a greater gravitational influence in the past, but due to the expansion of the universe, less so now?
It's a tug of war. So the issue is that in the past, the density of galaxies was less patchy. So everything was more evenly distributed. So the overdensities weren't that much over, and the underdensities weren't that much under. Over time, we've had two different things happening. The universe is expanding, which on average lowers the density of galaxies. But those overdensities have been getting much, much greater while the voids have been getting much, much emptier. So this interplay causes the overdensities to have a greater impact on the area around them than they would have in the past. But over time, with the expansion of the universe, the overdensities are getting spread out so that the effects that they have at the intermediate and larger distances is getting less.
So do you think that it's appropriate to call an object like, the Laniakea supercluster an object, because really it's flying apart thanks to dark energy faster than it can be pulled together? Like there's a certain size where these objects will never be attracted to each other through gravity.
So if something is currently a supercluster, I don't know the one that you're currently talking about, I have to admit that. If something is currently a supercluster, that implies that it's gravitationally bound together. And so if something is gravitationally bound together, I feel confident calling it an object the same way I call I feel confident calling you, who's nothing more than a whole bunch of atoms that are bound together in molecules that are bound together through various forces,
Mhm.
a human being. Um, it is a system of objects who are bound in a variety of ways. You have stars and gas bound into galaxies that are bound together into groups that fall together into clusters that merge together into superclusters and walls and leave
Mhm.
behind voids.
But if my component atoms were accelerating apart from each other at increasing rates and would never clump together again.
Then I agree with you that it's not an object. But if you call something a supercluster, that implies that the members of it are gravitationally bound together. So that's where I'm being confused by what you're saying. So you can have two superclusters that aren't bound to one another and are flying apart. Those two things are not an object together. But these things in this supercluster, which are gravitationally co-orbiting the center of mass of the supercluster or falling towards it, which is usually a type of orbit, if it's gravitationally bound together, it's an object.
Laniakea, that's the new super cluster that was identified in the last 3-4 months.
Okay. I
So you know how
missed
there's the you know how we have the Virgo supercluster,
it.
and you know how we have the Pisces. Oh, I forget what it's called, but there's like a larger complex, super complex. Anyway, so the Laniakea supercluster is a even larger structure.
Okay.
Yeah, and the
I've
idea
been
is
living
that
in planetary science
yeah,
rather than
yeah,
eighth
and so
grade.
the thought is that it's actually to call it a supercluster because, as you said, the parts of it are actually not gravitationally bound. They're actually separating, and they'll never come together. Is it still an object? That's all. But anyway, let's move on. You have no idea what I'm talking about.
No, I don't, because the words it. If I understand what you're saying, is the outer parts of it are actually on orbits, kind of like the large and small Magellanic Clouds, where they're unbound orbits.
That huge chunks of it are completely unbound. That's right.
Yeah,
Yeah,
yeah. So the center part would be bound,
yeah.
while the
And there is
outskirts
kind of a
aren't.
massive, a largest possible supercluster,
Yeah.
and then beyond that point, dark energy is what's driving the expansion of the whole thing. So, okay, not to be all doom and gloom, but this comes from Nancy Graziano, but as 67P approaches the sun with Philae on board and Rosetta in tow, are there any predictions as to the fates of one or both of these craft? Is it anticipated they will be cast off or destroyed as 67P becomes active?
Well, if Philae will probably be all of the above, or at least some combination. They purposely attempted to land it near an active region so that it could watch the activity going on. But I mean, it could only dig down so deep into the surface to try and attach itself. And there's a non-zero probability that whatever it detached itself to will become an active region. So Philae has always had its days kind of numbered. With Rosetta, they're actually planning to adjust. Orbit is too strong of a word, to adjust its trajectory as it weaves back and forth kind of vaguely around the comet. They're co-orbiting the sun. To adjust its positioning relative to the comet to keep it at a relatively safe distance. The comet is so far projected to not be a very active comet, which is kind of sad from well, it would be great to watch all sorts of amazing things happening, but it's safer for Rosetta if the comet's a little less active and it can get down closer, get higher resolution pictures. So they'll be adjusting the spacecraft comet distance as needed to try and keep the spacecraft completely safe.
Philae has a weight, not a mass, a weight of 1 gram.
Yes. It's so silly. Its escape velocity is 1.1 miles per hour, which I know I walk way faster than that usually. So
Yeah, so you can absolutely, if you were on the surface of 67P, you could absolutely jump off and fly off into space.
The analogy that came up on Twitter that made me giggle and startle the dog was Philae is essentially a flea on the back of a duck's head. I don't know if ducks get fleas. Maybe it's a mite. Um, and a mite or a flea could jump off of this comet if it expounded all of its jumping ability.
So do you think the chances are that Philae will be able to recharge its batteries in the coming months as the comet moves closer to the sun, as it becomes more active, or will it, get bounced off again? So this is
That one, I think if we don't get it back in the next few days, it's going to get increasingly more and more difficult to get it back. This is electronics that don't entirely like to be frozen. And so they do expend energy on trying to heat the spacecraft to prevent things from freezing. And expending energy to heat the spacecraft, if you own electronics, having it on expends heat. Its batteries got low enough that it went into standby mode. If it's getting enough sunlight, it'll come out of standby mode. The longer it stays in standby mode, the harder it's going to be to get it out.
right. So maybe it's going to get closer to the sun. It's going to get more sunlight. Hopefully, it may rotate on a few orbits that are going to give it enough sunlight to be able to let it start doing some minimum science again. I think it's going to be. It just continues the excitement of the mission. The tension continues.
There's a cool question on Twitter.
What's the question?
I'm not going to try Martin. Martin of the unpronounceable French-looking name that has more consonants than I know what to do with asks, if I put a chunk of ice in the center of a nickel-iron asteroid and heat it up to molten, will it blow up like a balloon or outgas? So if you heat it up till the metal's molten, it will just convectively get rid of the ice in the center. But if you heat it up to the point that the ice in the center undergoes a phase transition, but the metal is still attempting to be a solid, it will beautifully find a way out of the asteroid, which could either be a crack in a geyser, or if it's small enough relative to the chunk of ice, blowing up like a balloon. That could be a thing, and that's kind of cool to think about.
Okay, let's see if we got some more questions here. So Elad Avron says, I've read some places that the Philae landing was a failure 10 years in the making. I strongly disagree, but what are the numbers? How much science did Philae manage to squeeze in and send back before it went to sleep?
So the thing you have to remember is many of these missions have what I can only refer to as accessory spacecrafts. Huygens are like the pocketbook you add to your couture gown. There was Beagle on, I believe, Mars Express. There was Huygens on Cassini. These add-on missions are at an extremely low cost and are also fairly high risk. So these are the science things that we attempt to do because we're spending $1 bazillion on the main spacecraft, and comparatively they're like free, basically. And when they work, like Huygens did, like Philae is doing, you don't necessarily expect a whole ton of science from them. Huygens didn't last that long. We're still using its data. Philae, I don't think they've publicly released everything yet, and we're already starting to get amazing information coming out of it. Just go over to the Planetary Society blog, read all of the stuff Emily Lactowal is writing. It is justified. And the whole a mistake 10 years in the making, it performed perfectly for a spacecraft that had to be repurposed for a different shape object. This is the same level of complexity of trying to figure out how to land a 747 designed to land on wheels on a runway on the Hudson River. You can do it without loss of life, but it wasn't designed for it.
Right.
And they pulled it off, and they're to be commended for figuring out, with the fuel on board, with the technologies at hand, how to make this amazing approach and landing, because it wasn't designed for this.
Force 15 asks a question that has nothing to do with anything we've talked about so far.
Good with that?
How many exoplanets have been discovered?
A lot.
A lot.
There's a website.
Thousands.
Yeah, there's a website, exoplanets.org. That I'm now going to. Yeah, they
race ya. 1,492 planets
confirmed, but 4,875 confirmed and candidates.
Yep. So
I
there
think
you go.
I got to it first, but you spoke fast.
Yeah. We're at 4,875 planets have been
suspected.
Yeah, so far, like lots, and we're just getting started. The upcoming, is it the Gaia mission?
Yeah.
The TESS mission is going to really push this even further. They think they're going to find 20,000 exoplanets with TESS.
We need more spectrographs.
Yes. You know what would be great now would be some kind of spacecraft that is able to detect the atmospheres of these planets and, I don't know, find life.
Yeah.
If we were in charge, Pamela, we would have the,
If we were in charge, I wouldn't have spent 2 straight weeks writing grants. Sorry, I literally... I'm hyperactive because I left my chair today.
Yay! Pamela left her chair.
Yes.
All right, let's see if I've got anything else here that I think is useful. Nothing I see there. I'm going to look in the event page. So I want to do a pitch to a couple of communities, of course. First, the CosmoQuest community. If you want to, especially if you are working on CosmoQuest and you want to talk to the other people who are searching for craters and moons and craters on Mars and things like that, go to cosmoquest.org/forum. And it's a long-lived community that started out as the Bad Astronomy community, and then it became the Bad Astronomy Universe Today community, and it became the CosmoQuest community. So, all of our...
For any of you who were part of the community for all those 10 bazillion years, if you can get us the logo in high res, we're working on site updates, and we have people on the forums, but we know that not everyone goes constantly there. So I'm going to put out this added plea. If you haven't been on the forums for a long time and you're that person who developed that logo that had Phil Plait as an astronaut, I need that graphic.
Okay. Maybe I have it somewhere. I'll take a look.
Okay.
And then also the Weekly Space Hangout crew, which is a Google Plus community. And they're really active for the Weekly Space Hangout, but a lot of them I know are watching right now. So it's a great family to join. Small group, but really tight-knit, and they share a lot of cool space stories. So, now, Pamela, how can people find out more about you?
I live on Twitter. I am at Starstrider on Twitter. Why does every time you
lower third?
I use my lower third? That is a weird technology fail. Okay.
And I am F. Cain on Twitter. So if you want to follow me, F. Cain, you want to follow Pamela, Starstrider with a Y, and of course Astronomy Cast, Universe Today, CosmoQuest, Astrosphere, all of these things that we do, and a bunch of our friends. If I was to pick one person to follow right now, I would pick Emily Lakdawalla.
Yes, I agree with that.
Just killed it on this whole Rosetta mission. She went to Europe, reported. I think she gained like 5,000 followers over just like. Earned 5,000 new people following her. So it's E. Lakdawalla, and the work that she does on the Planetary Society is just astonishing. So follow her. Follow her, and if you have room left over, follow us. All right, let's wrap this up. So again, thank you very much, Pamela. Thanks everyone for watching. We will see you all on Friday with the Weekly Space Hangout. Wednesday, learning space.
Yep.
We're going to learn something about space. Awesome. All right, we'll see you all next week.
Okay. See you later.